It's easy to see the difference in the two graph representations just from looking at these diagrams. They're both representing the same graph. Depth-first search, no matter the representation, visits every node in the graph once. The difference between an adjacency matrix and a list is that in the matrix, each node is represented by an entire row of size n, and to find the adjacent nodes, you need to traverse the entire row. The list, however, stores at each node's position only the adjacent nodes, and so for each node, you only need to visit the number of edges, which all up are at most n. The correctness of the equation here in yellow, is built upon the logic of the three facts stated above. If a hotel n at block I, say n of I, can be reached by k distinct paths, each hotel one block beyond n, say n I plus 1, can be reached by taking any one of those k paths in addition to the road connecting ni to n I plus 1. A hotel on block I, say n of I, will be able to be reached by the sum of the k distinct paths that each of its neighboured hotels one block closer to the station, at I minus 1, can be reached by. And all of the shortest paths from the station to a hotel n at level I must have a length of I. And therefore, with W being a neighbour of n one block closer to the station, we have that the number of paths leading to n are the sum of the number of paths leading to all of the neighbours of n that are situated one block closer to the station. The usual breadth-first search algorithm will do the trick with just a little modification of the data structure storing the graph. If a paths count is included for each node, as the breadth-first search travels through the graph, it can add to the paths based on this above equation. The runtime is n plus m. Since we're using breadth-first search, which is n plus m time, we're updating the counter in m time, and there's an initialization in n time, so runtime complexity is still n plus m. Breadth-first search and depth-first search will visit every node in a graph only if the graph is completely connected. If there is some node or nodes that are not connected to the rest of the graph, this will be left out. So a normal breadth-first search or depth-first search can be used to test for connectivity. I've used depth-first search as my example. The only additional code added is the creation of a list of visited nodes, which is added to if a node is visited that has not yet been labelled as visited. And by the end of the search, if the length of the list of nodes is equal to the number of nodes in the graph, then the graph is connected. But if it's not equal, the test fails.